Okay, I guess it's time to start. Before I do any sort of introduction or anything else, like anyone who wants to like follow the tutorial with their laptops and actually do some coding, like please go to this URL h2oai.quicklab.com. Like, can everyone see this, or should I make it even bigger? You don't need like a GPU or whatever on your laptop. We're gonna work on AWS through this portal called QuickLab. So after you go there, you will see a join button, a sign in button in the right upper corner. So please make an account. Like you just need to fill out a few fields. You will get an email with activation link. So please do that. And after you do, you can sign in. And for now, that's it. Okay, so hello and thank you for coming. Way more people than I expected. My name is Mateusz, and I'm one of the software engineers at h2o.ai. Are people like familiar with the company H2O.ai or not really? Like a show of hands who knows the company? Okay, cool. So for the people who don't know us, we do machine learning platforms. Our original one was all in Java. It was a distributed platform. A few months ago, we started also working on GPU implementations of certain algorithms. And we figured that since GTC, the NVIDIA conference, is next week, it would be a good idea to do a CUDA workshop. The project I was talking about is H2O4 GPU. It's on GitHub, open source. You can check it out if you guys are looking for a project that you want to contribute to. We are always looking for new people. Okay, so did everyone who wanted to sign in, like, was able to sign in into QuickLabs, or is anyone having problems? No problems? That's perfect.
Use Chrome.
Okay, use Chrome. I used it with Safari, and it seemed to work okay, but yeah, Chrome is like the default one. Let me sign in. Okay, so after you log in, you will see a few labs. We will be interested in the CUDA one-on-one hands-on. So you just need to click it. You hover over the CUDA one-on-one hands-on and click it again. And you will see a big green button in the right-hand side corner. So you just click start and let it be. This will take quite a while because it's spinning up an AWS instance. Yes?
Can you show the link again? H2O.
Yes, sorry. Here we go. So for people who are already signed in and in the lab, click the link, click the start button, and just leave it be. Is anyone having any more problems, or?
So which one I will start? I got this one.
Yes, it should be CUDA one-on-one hands-on. It might be, you might need to scroll down. Yes, click on it, and you will need to click again on the CUDA one-on-one. I will post it on the meetup, but all those tutorials are on our GitHub. So don't worry if like you won't be able to like finish it all. Like I'm pretty sure we won't be able to cover everything I prepared because this is the first time we're doing this workshop, so I didn't really know how long it will take us. So after this is finished, and if you want to go through it again or like just finish it up by yourself, you can run it on any machine with CUDA installed. You can spin up an AWS instance. It's just like 90 cents per hour. So, okay. So is everyone good with the with starting the lab, or any more questions? Okay. Okay, so while this is like booting up, it will still take some time. I will start off with the theory and how this whole thing will gonna look. So this hands-on will be in a Jupyter notebook. Is everyone familiar with Jupyter notebooks or not really? Who hasn't used a Jupyter notebook before? Okay, no worries. It's nothing really special. It's so Jupyter notebook is just a notebook originally done for Python, but you can also run terminal commands from it, and that's what we're gonna use. So everything you will see will actually run on the servers, not in your browsers. So this will actually run on the GPUs. This is all heavily influenced by NVIDIA's cuBLAS and NVIDIA's programming guides, which are really good. If you want to go into more details, you should check those out. So a show of hands, like who has programmed C or C++ before? Perfect. Because this is, okay, so another question, like who already programmed in CUDA for C? Okay, so for you too, this might be pretty boring. Because this will be like a very, very brief introduction. We will be talking about CPUs and GPUs and like why would you actually even want to use GPUs. We will discuss for what you would want to use GPUs and for what CPUs. And since H2AI is a machine learning company, we'll also talk about using GPUs for machine learning because, well, that's all the buzz and all the hype nowadays. And we will actually write some simple programs. Is that still on? Okay. So after the lab finished loading, like you should see on the left side this Jupyter link. If you see it, you can just copy the link using the button or whatever, and paste it into your browser, and you will see this screen. Please don't reuse the Quick Labs tab. Open a new one because Quick Labs is not very smart. So after you're able to like see this screen, you will need to insert the password or the token, and the token is just H2O. Everyone good so far? Awesome.
I don't see the Jupyter link being generated. I see the username at AWS.
Is it still loading? Like, do you still see the? Yeah. So you will see it after it starts. So you just need to wait a little bit longer. And after you see the Jupyter notebook, there's the CUDA _101. You just click it and it will point you to the notebook. Ooh, let me see. Okay, can you H2O?
H2.
Oh, yeah. Oh, we good? Cool.
Is this not a notebook also on GitHub?
Yes, so this is all on the tutorials GitHub. So like the notebook, all the labs, everything is on the GitHub. So did the lab start for everyone, or is someone still waiting? Okay. Okay, then let's wait a little bit longer. Okay, I guess we can start with the CPU and GPU overview. Okay, this is like a very, very basic overview of like CPU versus GPU architecture. The image is taken from the NVIDIA tutorial. So as you can see, the basic architecture is pretty simple. There's on the CPU, there's the RAM memory, there's a cache memory, there's a control unit, and there are ALUs, so the arithmetic logic units, which actually do the computations, right? If you want to do additions or multiplications or whatnot, this is what actually does the job done. As you can see, the GPU architecture is kind of similar in a way that like it has the same components, but there's way more ALUs. Obviously, it's like not exactly the same. If it was, like we would just be using GPUs for everything. The main difference is that CPUs, like the processing units on CPUs, they are much more powerful. Like the clock rate is much higher usually. So if you have tasks that actually are long-running and need a lot of computations, but few of them, you usually prefer CPUs. Whereas if you have a lot of really, really small tasks that are not really computationally very, very heavy, you usually prefer GPUs because we will be able to spin up way more operations at the same time. The other problem is RAM. So like if you're using CPUs, like you can have like a terabyte of RAM nowadays, and that's not a big deal, right? With GPUs, the story is quite different. GPUs don't use your regular CPU RAM. They have their own RAM memory on the GPU card, and that is like usually much smaller, between a few gigabytes to I think the biggest one now is 16 gigabytes. So you need to think about that kind of stuff. There are ways to use the host memory, the CPU memory directly, but that's much slower. So usually, what we talk about when we're talking about CPU versus GPU is latency versus throughput, whereas CPU is optimized for latency. So as I said before, like if you have a few tasks, but they are long, they will perform better on the CPU, whereas GPUs are more for throughput, so if you have a lot of tasks. So whenever you want to write an application that is GPU accelerated, you don't usually write like the whole thing on the GPU because a lot of tasks are just not performant. Like if you have sequential tasks, you want it to run on the CPU. So usually what you do is like you look at your application code and you try to figure out which parts are compute intensive. And you just grab those and try to rewrite them on the GPU while everything else stays on the CPU. Does that make sense? Or okay. So GPUs in machine learning. So the thing with machine learning, at least with the basic algorithms, is that they are usually compute bound. What that means is that usually there's like more computation going on than fetching stuff from memory. For example, like I'm pretty sure you guys are familiar with Spark and like in-memory processing. One of the reasons why they created that framework was to grab everything into memory and just run iterations over and over again because, well, that's just much faster, right? And a lot of machine learning algorithms are just matrix multiplications, matrix summations, operations of matrices that are run in iterations. Yeah, as I said, like a lot of ML is just matrix multiplications. The drawbacks as I mentioned before, is you don't really use the host memory, whereas by host I mean like the CPU directly, so you are like bound by the size of data you can actually use. And you are really also limited by the instructions that can be performed on the GPU. Like the instruction set on the chipset itself is not as big as on the CPU. So you have to think about all of that when writing GPU code. So is everyone okay with like the notebook? Like, did notebooks load for everyone? Anyone has problems? Okay. So let's check if the notebooks actually work. For people who are not familiar with Jupyter notebooks, it's just a set of cells. If you click on any part of the notebook, you will see it will highlight that part. That's just a cell. Each cell has a type. The text ones are just markdown. Those gray ones are code, which you can actually run. And you can run it by either pressing one of the buttons or just pressing Control Enter. And I would want everyone to run that NVIDIA SMI cell by pressing Control Enter, and just to check if it works. So what the bank means is it will just run the command in the terminal. And NVIDIA SMI is just this NVIDIA command which will give you a lot of information about the GPUs that are on that machine. Everyone okay so far? Yep. As you guys can see, we are using an instance with one Tesla K80. It's not a particularly powerful machine, but it gets the job done. It has 12 gigs of memory, so way more than we need for this lab. If you want, you can run the cell below it, also with Control Enter. And after it finishes, you can download the zip file with all the labs and all the files required. But as I said, they are also on our GitHub, so you don't really need it. Okay. Okay, so let's get into the actual CUDA stuff. So CUDA is actually many things, but one thing that we'll be talking about today is this extension of C, where NVIDIA gives you this thing called NVCC, which is their compiler that will compile both the CUDA stuff and the regular C code and output you a binary. And also it extends C with a set of keywords and methods that you actually need to write that kind of stuff. So we will be using a little bit of terminology, some of which I already used. So whenever I'm talking about a host, I'm talking about like everything that's not GPU. So CPU, RAM memory, PCI Express, etc., etc. Whenever I'm talking about device, by device I mean the GPU. So like the basic idea behind CUDA is our kernels. So a kernel is just a special function that would be run on the GPU, and that's what we're going to be writing today. Contrary to regular C functions which just run in a single thread, CUDA kernels by default will be run in a multi-threaded environment. Like CUDA will just grab what we wrote and it will execute it on each of the ALUs that I was showing before on the on this screen. So basically, on every green square there will be a new instance. How we create kernels? We just take regular C functions and we prepend them with underscore underscore global underscore underscore keyword, and that's it. Then you just push the file to NVCC to compile, and you're done. There are two more keywords that you might use in the future or not: host and device. Host is just a keyword for a method that's run on the host, and it's called from the host. Device is a method that is, sorry for that, that will be called from the device and can run on the device. I will try to make it a bit more clear when we actually get to the source code. The second important thing about CUDA is like the threading model, because that's why we actually want to use CUDA, like multi-threading out of the box. So a few concepts that we need to know are obviously threads. I hope everyone here is like okay with what that is. Threads are then grouped in what is called a block, and then blocks are grouped in grids. This is both for convenience and both because of how CUDA is executing that kind of stuff. Blocks and grids, they can be one-dimensional, two-dimensional, and three-dimensional, which we'll be trying to actually use in one of our labs. This is all been made to make it easy to work with different kind of data structures. Like when you will be writing machine learning algorithm or graphics algorithm, you will be working with vectors, matrices, or tensors. So depending on which data structure you're using, you probably want to group them either in 1, 2, or 3 dimensions. Within kernels, you can get certain information about all that kind of stuff. So for example, if you want to write, and this will be our first lab in a moment, if you want to write a very, very basic summation of 2 vectors into a third vector, what you can do is you can group it in blocks. So let's say we want n blocks. In each block, we will have 2 threads, and this will all run in parallel. This is like a little bit of a paradigm shift. Like for me, this was the biggest problem when I was coming from my Java distributed Spark, whatever background to this, is that sometimes you need to switch how you think about it. Not from input to output, but from output to input. So for example, here, what we can do is we can make each thread calculate one output. So for example, each thread will be calculating one value in C, and then we need to figure out how to actually calculate it. With vectors, it's easy, right? We will be just summing the same values. But like as we will see in the next lab, it gets a little bit trickier with, for example, matrix multiplication. So why I'm talking about this is because for each of those, based on the block ID, the number of blocks, and the thread ID, we will need to calculate which cell each thread will be working on. And those values you can get using a few CUDA supplied values: thread IDX, block IDX, and block dim. Those are all vectors with 3 values, x, y, z. Block dim, which is like for block dimension, is a constant. It will be the same at every instance. The other 2, they will change depending on which thread we are working with. Okay, let's get to some actual coding. So let's start with the the most basic C program you can write. So if you go to lab 0, there's a link to lab 08C file. There's not really much to see. I just want you to like see how the editor that we will be using today looks like. And you can run this fascinating program to just see that it works. So as an introduction, I'd like us to see how a similar print program would look on CUDA. So if you compare this one with this one, okay, you will notice like those few things that I was trying to like talk about before. First, the global keyword, which will make our hello function a kernel. Like this is it. Like this is everything you need to do to make a function a kernel. The second thing you will notice is that the invocation of the hello method changed. This is the syntax for launching kernels, triple pointy brackets. And inside, like there's a few ways you can use this. Like this is the most basic ones, which says the number of blocks and number of threads. So this will just run on one block, and in each block there will be one thread. If you want, you can actually change those. You can try out like different values. And the third thing you need to notice is the CUDA device synchronize method. This is there because kernel launches are asynchronous. So this means that when we will get to hello, we will run it, and it will push all the stuff to the GPU. So it will push that kernel to the GPU, and the control will come back to the host code before that thing might actually run, and we might be able to return before it executes. So to make sure that the kernels actually run and like finish, we need to first synchronize all the devices, and that's what the method does.
So you have printf. Do we have access to the whole C standard library within a kernel, or?
No. So printf is actually, like Rory might know, so like the guy standing in the back, like if you have like very hard questions, that's the guy you should be asking. Like I've been doing CUDA for a few months. The guy is, does anyone know XGBoost? The library? Okay, so that's the guy who wrote the GPU version of XGBoost, so he's like very smart and very jet lagged. But from what I understand, printf is a pretty new thing.
To answer that question, I think printf is a special case in CUDA.
Right.
Apart from that, you can normally expect to use math functions, and that will be fine, and certain other things, but you can't guarantee everything that's in the C standard you can use.
Cool.
Exactly. Okay. Any more questions for this extremely interesting piece of code? No? Okay. We will get to more interesting stuff, don't worry. Hopefully. Yeah, so you can try and run this. So here we will be using NVCC, which is the CUDA compiler supplied by NVIDIA. It does a few things. It compiles the device code, and compiles the C code. On this machine, I think it just uses GCC. It binds it all together into a single binary, and it runs on the device. So like a few things you can play around with is you can change the values in the brackets and check what's going to happen. Like you can change the number of threads, the number of blocks. Like for example, if we get here 32, after changing stuff in the editor, be sure to save it. On Macs, it's Command S. On other platforms, I guess it's Control S. You will see a tick box next to the name of the file. And then you can rerun the whole thing. So this ran in parallel on the GPU with 32 threads. Actually, I want to show something a little bit different. Okay, one thing you need to be aware of, is that those thread invocations, every single invocation is actually not related to each other. So one thing you need to also think about while writing those programs is that there's no set order. So for example, if you have problems that heavily rely on the order of operations, you need to either try to figure them out somehow differently, or you need to do some kind of synchronization or atomic adds or some kind of locking, etc., etc. Because in this case, we see all the numbers increasing, but they actually could be jumbled up. Like you could see thread 64 first, and then thread 0, etc., etc. One more thing you need to be aware of is that currently the maximum number of threads per block is 1024. So if you would use 9000 here, it should fail if you try to run it. The thing is, you won't see anything because we don't have any kind of error checking, which we will do in lab 3 if time allows. So yeah, the max is 124, but then again, you can have as many blocks as you want, so you still can have as many threads as you want. Okay, let's code something actually interesting. Okay, let's try to write our own addition program where we will try to add A to B, 2 vectors, and put it in C. So if you go to lab 1, custom kernel, and click on the link lab 1 ACU, you will see we already prepared a lot of boilerplate for you. You don't really need to look at the main function. Like we will try to go over this in later labs. There's a little bit of memory management and figuring out how many blocks and threads we actually need. What you want to focus on is 3 things. First of all, make this function a kernel. Second of all, as I said, every kernel, so every invocation of this method will be working only on one cell. So what you need to figure out how to do is how to calculate the local index. And to do that, you will be using the values I mentioned before, the block idx.x and thread idx.x and blockdim.x. So using those 3 values, you need to figure out which one we will be using. And I'll grab this. Oh, awesome. So this will be your whole pool of threads, right? So in this case, if you try to use the values, the block dim.x will be n, and this is constant. Then the block idx.x will be 0 for this block, 1 for this block, 2 for this block, 3 for this block, etc., etc. And the thread idx.x will be either 0 or 1 for each, right? So what you want is to calculate that the block 0, thread 0, will be working on index 0, right? In block 0, on thread 1, you want to be working on cell 1. In block 1, in thread 0, you want to be working on local index 2. Here you want to be working on 3, etc., etc. So using those 3 numbers, the block dimension.x, which is constant, block index x, which is 0, 1, 2, etc., etc., and with thread x, you want to write an equation that gives you this value. Does it kind of make sense, or like should I make it more clear? Does anyone have any ideas, an idea how to do it? Okay.
So I'm assuming we're going to check the number of blocks.
Okay.
Sorry, the dimension of the block.
Okay.
Multiply it by the block index.
Right.
And add the thread index.
Okay, so almost. So the first part would be to multiply the dimension of block, yes. Then by the index, this will give you the starting points, right? Does everyone see how that works? Like if you have, for example, let's forget about these guys. Let's go with only this 3. So your n would be 3, right? Then if you do block index here, which is 0, by 3, this gives you 0, right? So we're almost there, but you also want to handle this and this, right? So you need to add also the thread index. So what you need to do is you need to multiply the block, this guy, block dimension x times block index x, and this will give you the starting points. And then you need to actually go through that block, and that you can do using this guy, thread index x. So you just need to add it to that. Does it make sense?
Do we need to verify that the y and the z are zeros?
No. So this is all given to you by CUDA, so it will just be 1, so that's okay. In this lab, you don't really need to go through this. One thing that you need to actually sanity check is this part, because what if your number of blocks and threads, like you cannot divide it by the size of the index, right? By the size of the whole vector, right? So for example, what if this will be, for example, 13, right? Like there's no way, I mean there is, but it would be only like 1 block with 13 threads, right? Usually you want to make it generic enough to handle all the cases. So one thing that can happen, you can actually run way more threads than you have elements in the vector, right? So you can so you actually need to sanity check that this value won't give you an array index out of bounds, right? And in our case, we just hard-coded it to n16, so you can use this value n here to make sure that it won't like go out of bounds. For people who have no idea what this crazy Paul is talking about because he's still way too jet-lagged, there's actually the solution here in the link. But I can give you a little bit of time to try and figure it out. Okay, so the first part, I guess, I hope, is pretty simple. You just need to add the global keyword. So this will make the whole method a kernel. Let's start with the sanity check. So if you don't want to get here an index array out of bounds, I hope that's pretty reasonable to do something like this, that n, that local index is smaller than n, right? Because if it's bigger, then we will just go out of bounds. And for the local index, okay, so as we mentioned, we will be using the block dim x times block index x. So this will give us those starting points, right? So block n times 0 will be 0, so we will be starting with index 0, right? 1 will be, we will go through this, so we will come to this guy, then by 2, etc., 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 right? So we already covered this. What we need next is the next one in the block, the next one in the block, etc. So as I said, like this is every cell is handled by one thread, right? So we can use the thread values. So we just need to add thread index.x. Does it make sense? Like, does everyone see where am I getting those values, or should I go more in depth? Okay, I will try to explain it a little bit more. So every add method will be invoked on one processing unit in the GPU, right? So this block dimension x will be what we were declaring in the, it was here, I think. It was here, right? So what this says is that we will be running on 2 blocks with 1024 threads. So in this case, the block dimension x would be always 2. Then there's the block index x, which is different for each block. So out of those 2 blocks, there will be a block 0 and block 1. And then at the end, we will have thread index x, which will be ran inside each block. And it was this part, right? So here we declared 1024 threads in each block. So we will have thread x 0, 1, 2, 3, 4, etc., etc., etc. Is it like a little bit more clear or not really? Yes.
So blocks, are they like hardware constructs or are they logical constructs?
No, that's a logic construct. There are hardware constructs called warps, but I don't really want to get into those. But yeah, this is like all a logical construct. Like how this is actually ran is on the GPU. There's this thing called the streaming multiprocessor, and SM, and it's like an actual thing on the GPU. It will take our program and it will try to schedule it on the GPU. So it will take that one block, second block, and put it on the GPU. And this is important because depending on the GPU, different GPUs have different numbers of SMs, right? So this is a logical construct that makes our life easier because it just scales automatically, right? If you will run it on a GPU with less SMs, it will schedule it like this. If you run it on a GPU with more SMs, it will like automatically schedule it so more blocks run together. Because even though we say, for example, that we want 1 million blocks, right? A GPU won't be able to handle them all. So it will only run as many blocks as it can at the same time, and then just schedule next one, etc.
Is there a per block overhead?
Sorry?
Is there a per block overhead? Why don't I just use all? Why don't I have one thread per block?
Yeah, there's going to be an overhead. I don't know how big it is, but maybe Rory has like more numbers. Rory, is there like a per block overhead? Is there a per block overhead? I mean, it depends on like how many blocks can be scheduled by an SM, right?
So the number of blocks that can be currently scheduled depends on, for example, how many resources are available on the GPU, which things like how many threads you launch and how much shared memory is available, and that's called occupancy.
Right.
So it does vary, but there is a maximum amount.
Well, yeah, but if I remember correctly, it's like it doesn't really check like how many threads you have also inside, but more about like the blocks, right? So if you have like a lot of small blocks with small amount of threads, it still doesn't care, right? Like for the GPU, I think it's the same if it has like 5 blocks with 1 thread or 5 blocks with 1,000 threads, right?
Something like that.
Yeah. So it will be just slower, right? Because it doesn't check the total, if that makes sense. No? Okay. Okay. Okay, so with those changes, hopefully it will run. Not this one. This one. Of course, forgetting comma somewhere. This guy. Blah, blah, blah. 14.
Is knowing which block your thread is running in, is that important?
Sorry?
Is knowing which block your thread is running in, is that important?
Yes. Yeah, usually you need to use it like in this example, because you just use it for indexing, right? So all those values, like in which block you are, in which thread you are, and like how many, like what's the general dimension of blocks. That's usually what you use to like figure out on which block you need to sell. Well, you need to work.
When do you need to know that though? Like in what use cases?
Well, for example, like in this one, right? So if you want to calculate on which cell you want to work, right? You will need all of those. I'm trying to figure out a way to explain it more visually, maybe. Okay, without knowing that, like, how would you, let's say you want to sum those two vectors, right, into C. Like, without that knowledge, how would you want?
Okay, I see what you're saying.
Right?
Yeah, I get it now, yeah. So if you're going to do a calculation, then you might need to know which block it's in
Because that's what tells you, like, which cell you will be computing. Yeah, exactly. And as I mentioned, like before, like so how we're launching this kernel is like all one-dimensional. So it looks like exactly like this, right? You have one dimension of blocks and one dimension of threads, and we're doing it exactly because we're working on vectors, right? Like the mapping between those values and the index of the cell is pretty straightforward, right? But as we will see in the next lab, like if you're working on matrices, like you can actually launch those kernels in as two-dimensional now, like grids, or even three-dimensional, which also makes it much easier to map. No worries. I'm just trying to figure out what's the error about. Okay, I will cheat a little bit so I don't waste your guys' time. Okay, I had the typo. Okay, so the final solution should look something like this, the block index. So this is the index of the current block that we will be in, times the block dimension, like the total dimensions, plus the thread that we are in. And using this local index, we know like which values we actually need to sum. Like we want to take that local index value from A and B, and we want to put it into C. And let's see if it actually works. Okay. Yeah, so the outputs seem to work pretty well. And like one thing to notice is that every value was computed by a separate thread, right? So now if you wanted to run it on a much bigger vector, it will scale for you also automatically. So does this make like any kind of sense or? Sure.
You don't have to synchronize for the main.
Sorry?
You don't have to synchronize for the main.
Here I think I. So no, here I don't, because certain calls here are already synchronized. This is something I will be talking in the next lab, that, for example, the CUDA mem CPI, this guy, it's already synchronized. So this is something that, unfortunately, you as a developer needs to know. Like, you need. I will go into details in the next lab. You will see why.
But would it hurt to add an explicit synchronize?
Sorry?
Would it hurt to add an explicit or accidental overhead to that?
No, not really. It's just that, like, in this case, you don't really need it. But no, I mean, overhead. Well, you need to wait for it, right? So that's your overhead. In many cases, you just don't want to do that. Like, especially if you like run on a multi-GPU system, like you really don't want to do synchronization that much. Like, especially in your host code, like you need to watch out if you do. Usually, how you do multi-GPU stuff, you just will run this in a for loop over the number of GPUs you have. And if you do synchronize here, like all the other GPUs will also stop. So this is actually one problem that we had in our H204 GPU code, and it was like a huge bottleneck. So there are ways, obviously, to overcome it. For example, with MPI, like you can just add a pragma that will run this in a separate thread, and you're good, right? Like, or you can explicitly run this in separate CPU threads, right? But you need to watch out for that kind of stuff. Okay, there's an easier way to do this. So like if what I just told you guys like completely didn't make sense and like it was a horrible explanation, don't worry. There's an library called Frast. Are we familiar with STL? Yes? No? Okay, so for people who are not familiar, STL is a standard template library in C++. It gives you a lot of containers and algorithms out of the box. And Frast is kind of modeled like that. It doesn't have all the goodies, but a lot of them. So, for example, there's this container called the Frast vectors, which is more or less the same as the STL vector. And in this lab, we will actually use those vectors to do the same thing we did just now. If you go to the lab 1B CU file, which is in the Frast paragraph, you will see that the code is like much easier. So you don't see all those like CUDA allocations and like no freeze and like there's not even any kernel, right? So you don't really need to write kernels if you want to write CUDA code. The invocations are pretty easy. To declare vectors, you just use the standard C, C++ notation, where we will have A, B, C as device vectors. So Trust has two types of vectors, host vectors and device vectors. Host vectors are, well, just like normal STL vectors. They are on the host, and you can do whatever you want on the host with them. Device vectors, if you want to run stuff on the GPU with them. So we will declare 3 of them, each with size n. The good thing about Frast is like that you don't need to allocate and move the memory explicitly. It's all done implicitly by Frast, so you can just use them as regular C++ vectors, and you can just assign values to it, and it will automatically take the values and push them to the GPU. So what we want to do now is use those vectors to do exactly the same thing we did before. So Frast has this set of library algorithms. One of them are called the transformations, and we will be most interested in one that is just called transformation. Sorry, transform. If you go to the to this link, the Frast transformation methods, it will give you the API. With a whole bunch of methods. We are interested in this one. The one with first input iterator, last input iterator, the first 2, output, and binary function. If you find it and click on the on it, you actually can find the solution to the whole lab. So the cool part about Frast is that you can use iterators and just do what we were doing before. So the other way to think about vector addition is to think about it as a transformation of 2 iterators, right? So you will go from left to right, cell by cell, and just add adjacent cells, right? So this is exactly what transform does. It will take the one iterator, the beginning of it and the end, a second iterator, the output where you want to put it, and an operation that you want to do on the first one and the second one. So operators, like, you can either write one yourself as a closure or as a structure, or you can use one of the predefined Frast ones. And this is exactly the one that we will be using, Frast : plus integer operation. So the only difference, so you basically need to take this, put below your to-do, and the only thing you need to figure out is how to actually get iterators, right? Because for now, we have only the Frast device vectors, right? And we need iterators. For people who are accustomed with C, C++, this will be pretty natural. You just do a begin, a end. This will give you the beginning of the iterator and the end of the iterator. Then you do B begin. Then you need to figure out where to output it. C begin. And we already have the operator, so this should be it. Let's see if it actually works.
Can you use C++ lambdas in place of like for instance the op here?
Yes.
You can?
Yes, you can. You cannot do everything with them. Like you cannot really. What was the issue I was having? You cannot use like lambdas inside lambdas too much, because with that you will have issues. But otherwise, yes. You need to prepend it with the __ device __ keyword. And there's also a few other catches that you need to watch out for. Like it's mainly about like how you pass the variables from like outside the lambda into it, right? Whether it's exactly. So you would need to read on about that. But apart, you can. Okay, cool. Yeah, so the result is exactly the same. As you can see, like there's like no kernels, no mem allocation, no nothing. Does this part make sense? I guess it makes a little bit more sense than the previous example. So basically, how this transform works is, let's assume this is our device vector A, this is our device vector B, this is our device vector C, and this is when we do a.begin, it will like give us the pointer to this. If we do a.end, it will give us a pointer to this. If we do b.begin, it will give us a pointer to this. C begin this, and what transform does is it will run the operator that we passed to the transform method and run it on this pair and output it here. It will run the operator here and output here, etc., until the end of the A iterator. Does it make sense?
And we don't need to explicitly, using Fast, we don't need to explicitly specify the number of blocks and the space.
Yes, exactly. Fast just takes care of everything for us. And the other good part is that it not only like takes care of that kind of stuff, like most of the algorithms that are implemented in Fast, they are already implemented with this kind of model in mind. So for example, like you might find like summation of numbers pretty easy normally on CPUs. Unfortunately, on GPUs, it's not that trivial, especially if you're working on floats. You can overflow, right? And the thing with overflowing, it's okay on CPUs because it's all sequential, right? With GPUs, as I mentioned before, like all those kernels, they can run in any order, right? So with each invocation, you can actually get a different overflow error. So you will be actually getting different results. Most of the Fast algorithms are actually implemented so it like tries to minimize that. So for example, there are algorithms that like do it in a tree fashion or like other ways that try to minimize it. And usually it's much smarter than just a brute force approach. So if you can use Fast, use Fast. It will be usually a bit slower than what you could handcraft with kernels, but I think it's a good trade-off.
How hard is the overhead?
I guess it really depends on the on which methods you are using.
When the two vectors are of unequal sizes, how does the iterator approach?
Sorry?
When the two vectors are of unequal sizes.
You will most probably get like some exceptions, like memory exceptions or stuff like that.
When if you could first, so you create the device vectors and then you go through a loop to assign values to them.
Right.
So with every assignment, it's handling taking the value and moving it to GPU. Is that handled?
If I remember correctly, it's like a little bit smarter. It will just batch it and just wait for the first use and then push it all like there. So it's like, otherwise it would just, yeah. Any other questions? Okay, how much time do we have? Okay, we still have like an, oh. No worries.
What if I dynamically allocated the device vector and forgot to destroy it? Will the memory in the GPU leak?
Yeah, it can. Like that's why here I'm using the heap operator. I guess that's what it's called, right? Like I'm not allocating the vector myself, right? I'm making sure that C++ just makes it on its own. But yeah, if you would here instead of like CN, right, do equals new device vector, and you would forget to then delete it, yeah, it would just stay on the GPU and it would just like sit there. Probably you would get an out of memories at some point. So you need to watch out for that, yes. Just like with any other C++ or C.
Well, but with C++, the memory is released after the program crashed. If this program crashed, the leaked GPU memory will still.
Oh no! It will get released with that. Yeah. So it's the same until the crash. It will be there. It will be leaking, but then it will just crash. Okay. Okay.
Can you run lint on this program?
Can we run lint, Rory? Yes.
Can you run lint in the sense of like, can you use a coding standard and this kind of stuff? Yeah, you can.
And what about purify?
I don't know.
Okay.
I think it will get a little bit confused when it sees certain CUDA constructs, but in general it will work.
Okay.
All right. So the question was about lint, and for people not familiar with lint, it's just like a syntax checker that will tell you if you're doing something really bad. And you should use it in your in your code. I'm laughing because we still don't have it ourselves, but it's a high priority for us. Okay, then let's move on to. Actually, we don't really have that much time, so for now I will skip matrix multiplication. Matrix multiplication is actually a pretty interesting problem because it's like vectors, but you need to work on a 2D matrix. But if we have time, I will go through it step by step. So one very important part of CUDA is like error handling. Like if you don't add error handling into your code, like you will suffer and you will really want to quit coding in it and like just be done with software engineering. In general, it's from my experience, it's even worse than C++ because C++ will give you like bad errors, but at least it will show you an error. With GPUs, as I showed in the in one of the first labs here, if you try to run a kernel with more threads than it's allowed, and you will try to run this piece of code, it will just show you nothing, right? It ran and it's like, okay. So you have no idea what's going on. So that's why you really want to do error handling. And there's a few ways to do error handling in CUDA. So there's the synchronous version and the asynchronous version. So So that was the question about like why I don't need to do the CUDA device synchronize, and that's because certain methods are already synchronized by default. And how do you know whether a method is synchronized or not synchronized? Well, you need to go to the documentation and you need to check the return value. If the return value of a method is CUDA error _t, it most probably means that it's synchronized. So for example, one type of synchronized method is CUDA malloc. So what CUDA malloc is just like malloc in C++. It will allocate some chunk of memory on the GPU and give you a pointer to that memory. If you run this, the error code will be your status. If it's CUDA success, this is a value that you just get from CUDA, then it means there's something wrong. So this is the synchronous version, which is easy. The other thing is asynchronous calls. So as we said, kernel launches are asynchronous, right? So you will run this and it will like send stuff to be ran on the GPU, but it will immediately come back to the host code, right? So even before this part is finished on the GPU, the control will come back here. So what you need to do then is you need to actually run CUDA device synchronized, and it will return you the error code, the last error code that was on the device, and you need to check that. You can also use some methods such as CUDA get last error, which basically just does the same thing. So since we have only like 15 minutes, let's go through the lab together. So this is our addition method. Like the kernel itself is already implemented. But what we want to do is we want to make sure that after this add, we want to do error checking. Because, again, if we have threads per block 9,000, it will just crash and not tell us anything. So what you can do is you can take the code from here, put it after the kernel launch, take also the synchronous one. Okay, so this should like cover, okay. Yes, I know, I'm really good at naming. This will basically cover all our cases. So the first one, CUDA get last error. This is like an asynchronous call that will grab the last error that got called by the GPU. So it will grab all the asynchronous errors, such as like if we exactly have improper values here, then we will wait for it actually to finish, and we will check if the values are okay or not. So hopefully with this, we should be able to see or not. Okay. Okay, this is okay. Okay, So after adding those two error codes, we can see that if we try to use way too many threads per block, then it's actually allowed. Finally, we will get the kernel error invalid configuration argument. So this is still not like the best error message you could get, but it's better than nothing, and you usually can Google it and figure out what's wrong. So invalid configuration argument usually means that what you pass to the kernel launch is incorrect. So usually what you want to do with those error checks, you usually want to write a macro or like a method that will grab this, and you can just wrap every call with it and be done with it. You really want to do it like very early in the project, because otherwise you will just forget about that kind of stuff. Okay, so memory management is something I would really want to spend a bit of time talking about. So as I mentioned at the beginning, so like in the computer, like usually you have your CPU, right? You have your host memory, which is like your RAM, like 1 terabyte or whatever. And you have a GPU, which also has its own RAM memory, let's say between 4 and 16 gigabytes, depending on how rich you are and how many the cryptocurrency miners bought. On every GPU, as I said, like this is the green one is the grid. So going back through to our example, right? You will have those grids, which will be green, blocks blue, and threads red. So you can think about it exactly in the same way on the GPU. Every grid, every block, and every thread have access to the global memory. And this is cool, but it's still not as fast as possible. So on the GPU, there's also this notion of shared memory. So every block has like a very, very limited number of like space that they can use, and it's much faster. So usually what you want to do is you want to abuse this. Like you want to grab data from here, put it here, and make all the threads within a block use this. So all the threads in this block can use this shared memory, all the threads in this block can use this shared memory, etc., etc., etc. And how memory management on the GPUs work is, well, you have to, just like in a usual C++ program, you need to first allocate the memory in global memory using CUDA malloc. Then you need to actually grab the memory from the host memory and pass it to the global memory of the GPU. This is all done by the CPU. And this is one of the biggest issues on GPUs. This is not free. This is going through a PCIe bus. So this is slow. If you have computations that are very, very fast, both on the CPU and GPU, like this overhead will kill your performance, and there's basically nothing you really can do about it. This is why some computations and some algorithms are just better done on the CPU. On the other hand, if you have like stuff like machine learning algorithms, which will be run on like hundreds or thousands of iterations, like this overhead might be worth it. Okay, so yeah, those are the main methods. Invocation is pretty standard, like just like in C, you have CUDA malloc. You need to get a pointer, just a C style pointer. You need to say like how big it is, and this pointer will be allocated not on your host, but on the GPU, and you can use it there, and only there. Like you cannot use this in your regular C code. I mean, you can, but you will just get garbage. Then you need to copy the data from host to GPU. This can be done either in a synchronous fashion, so this is synchronous, or you can do it in an asynchronous fashion if you wish so. One thing you need to remember is you actually need to, unfortunately, say like from where to where you're sending the memory. There's a CPU, mem CPU default for certain GPUs where you don't need to specify whether it's from host to device or from device to host. And yeah, so that's the basic one. From CUDA 6, now we're at CUDA 9.1, so some time ago, they added this thing called the unified memory something, which basically means that you can take one pointer, do CUDA malloc managed, and then you can use this anywhere you want. You can use it both on host code and both on device code. So in the previous snippet, as I mentioned, if you take this def_a and try to use it on the host code, this will fail. In the managed version, like this is smart enough to actually figure it out whether it's on the host and GPU, and it will automatically move it around for you. So what you can do is like you can malloc it here, you can initialize it in your host code like we did with Frast, and then you can pass it to your kernels, and what it will do is CUDA will automatically take it and copy it, so you don't need to do the CUDA mem CPI. This usually is pretty decent, but obviously there's a little bit of overhead, especially if you want to go like more into in depth and start doing it asynchronous by yourself. Do we still have time? We have time until like what, 8? Yeah. Okay.
Question.
Sure.
In the managed memory, are they synchronous? So like if one value changes in the array on the device, is that reflected right away on the
No, so it's like with Rust. So even though you initialize stuff here, right, it waits until it actually needs to move it. Same with if you change it on the device, it will wait until you actually use it on the host.
So anytime you make change on one side, it has to synchronize with the other side.
If you want to use it on the other side, then yes. Any more questions? Okay.
Yeah, so when you, I'm going to go off into the weeds a little bit.
Sure.
So when you compile a .cu program,
Right.
only the kernel code runs on the GPU, right?
Right.
The stuff that's global.
Right.
So all the things that we had in main, those run on the CPU.
Exactly.
And you compile these things with that
NVCC, yeah.
So can I compile like regular C++ programs with that? You know, that use, Boost or I mean, am I limited into what kinds of C++ I can compile? I mean, it's going to run on the CPU, a lot of it.
No, you can use whatever you want because NVCC does like two things. It will like figure out which parts of code are like the kernel one, the device code, and it will compile it by itself, and everything else will be just compiled by your standard C compiler like GCC, or it depends on the platform, right?
Oh, okay, so it uses GCC to
yes.
compile the CPU.
Right. And then it just binds it together and makes a final binary.
Okay, cool.
Any more questions? Okay. Okay, since we only have like 5 minutes, I might just finish there because we would need to go back to the matrix multiplication, or we can just have a look at it really fast. So with matrix multiplication, one thing you'll notice is we will have this matmul kernel, which would be just the global one interesting thing is that when you will look at the code and check the invocation, the values that we actually pass here, like before they were just integers, right? 1, 2, 3, etc. And that would give us a one-dimensional computational model, right? So it would give us like this kind of thing, right? It's all in 1D. But if we're working on 2D matrices, like it would probably be easier for us if we had like blocks going here and here, creating a grid, right? With threads also creating a grid, right? It would be much easier for us to map those threads to the indices, because what we'll be doing now is we will again use one thread to calculate one output of the matrix multiplication. So just to recap your high school math, like when you're doing matrix multiplication, you will multiply this row of the first matrix by this column, sum it up, and it will give you the output matrix, right? So if we only had like a one-dimensional number of threads and blocks, etc., right? It would still be possible to do it here. Like you would still be able to map 1D to 2D, but it would be just much harder. Like usually it's easier to do it in a 2D grid. So what CUDA allows us is there's this structure called dim3, and that's just a vector of 3 numbers, x, y, z. You can initialize it exactly like this. So what this would give us is a block of 16 times 16 times 1 dimension. So a 2D matrix of 16 times 16. And then you can do the same thing for number of blocks. In this case, if you have a matrix, right? Let's assume for brevity's sake that this is a 64 times 64 matrix, right? If you have 16 times 16 threads per block, it would be here to here, right? So now what you need to figure out is how many blocks you need to actually compute all the matrices. And how you do it is you just take the height of the output matrix, you divide it by 16 and do the same thing here, and you will get again like the number of blocks. Does it make sense? No. Okay, so if you try to map this image where you have blocks and threads per one output, so you will have one thread per one output in the vector. Exactly the same thing you want to do here, right? So you want to have one thread per each column. So the first structure you want to figure out is the number of threads in the block. So let's say that in this case we want to have 2-dimensional blocks of size 16 times 16. So one block will cover for us 16 times 16. If this is 64 times 64, it will only cover 1/4. Does it make sense?
So why don't we do like 64 by 64 blocks with one thread each?
So this was the question before, right? Like you don't want you don't want blocks with a small number of threads because there's a limited number of blocks that can run in parallel on the GPU, right? So usually you want to have a good balance. So in this case, for example, we hard-coded that we want 16 times 16 threads in one block, and we need to figure out how many blocks we need to compute the whole thing. Like it's similar to this example. Like if we we first assume that we will have 2 threads per one block, right? If we have n number of elements, then we will need n divided by 2 blocks, right? Doesn't make sense now? Actually, this is pretty confusing. I just realized now. This should not be block n minus 1. This should be block n divided by 2 minus 1, right? Because that will make sure that we will be able to compute every single one of those. So we need to do the same thing for here. We need to make sure that every single cell will get computed. So at the beginning, we assume that we will have 16 times 16 threads in one block, and we just need to compute enough blocks to compute the whole thing. So how this is done is, in the number of blocks, you will get n divided by this value, threads per blocks, x plus 1. Like this. This will make sure that there will be enough of them. The other thing you need to do is you need to calculate the row and the column that we are working on in each instance. And this is exactly the same as we were doing before, with the difference that we will be now using the block y and block dim y. Yeah. The rows would be exactly the same as in our vector example, and you need to sanity check it for row and end goal. That's it. And yeah, that's the whole code. Like, I wanted to go through one more thing, but I guess we're out of time. Any more questions? Does this like, okay.
Yeah, what usually determines the maximum number of blocks you want to set? I mean, does it depend on the GPU or whatever, or the system you're using it, or like is like 1,000 blocks okay? I mean, I'm not sure what the what the heuristic is there.
Sure. So usually you need to make sure that like you have enough blocks to cover like your whole data set, right? So that's why I usually start with the amount of threads, because first of all, like you don't really have that much wiggle room with threads because only 1024 are the max, right? So if you figure out like how many threads you want, then you just take your data set size and you just divide it by the number of threads, right? If it's like a million blocks, then
Right. Okay. So if it's a million blocks, then it's a million blocks, and then when the system deploys it into the GPU, it'll just figure it out.
Right. So depending on this on the GPU, there's like a different number of blocks that can run in parallel, right? So sure, you would probably want to figure that out, but it really depends on what you're gonna be running it on, right? So, for example, like you cannot go with too few blocks if you want to do like performance optimization or whatever, because if you figure out that like you want 16 times 16 threads in one block and you just hard code it to one block, then it will only compute this part, right? Because you will have only one block. And there's only 16 times 6. Okay, let's go with a smaller number. If you want 4 times 4 threads in one block, that means there will be 16 threads, right? And if you tell the GPU to run only with one block, it will just do that. It will just spin up 16 threads. And every thread calculates one cell. So you will only calculate 16 cells. If this is a bigger matrix, right, that means that like all the other cells are not calculated. So usually what you take is like you take the dimensions of your data set and just divide it by the number of threads, and that's your number of blocks. Does it make sense?
Yeah.
Cool.
So when you have programs with CUDA-specific code, there's some CUDA-specific libraries when you're compiling the link step to create the executable, correct?
Right.
And so when you write targets in link files, can you use the -L syntax and the targets and then the macros and all like you normally do?
Yes. Yeah, it's like just C++, yeah.
Is there a limit on number of blocks?
No, you can have like as many blocks as you want, but there's a limit on the number of blocks that will run in parallel. Because otherwise you would be limited with your data set size, right? Any other questions? Okay, cool. Thanks for joining. Sorry for it being so hectic. Like, I would love to hear some feedback, like which parts were like very, very unclear and which parts were only unclear. So if you could like email me, because I probably want to do it in the future. Thanks.